Lesson Plan 6 is going to be a departure from the topics that we've covered up to this point. We've spent a lot of time talking about columns, and we're now going to transition into a discussion of bending members, or beams. Another word for that is flexural members. And our discussion about beams is going to be divided into 3 different lesson plans, of which this is the first. One of the first things I want to get out of the way is to make sure we're all on the same page with what I mean when I say a flexural member or a beam. And I've sketched a very simple schematic, or included a sketch here of a very simple schematic of a flexural member. And one thing that we note about this beam is it's being loaded perpendicular to its longitudinal axis. So here's the longitudinal axis. The load is being applied perpendicular to that. And the effect of that is that the primary stresses that are being induced in this section are bending stresses. And that's really the fundamental basis for our definition of a beam. A beam is just a structural member that has loads oriented perpendicular or transverse to the longitudinal axis of the member. And the result of that is the primary stresses are due to bending. Now, back in basic strengths, you discussed how to solve for those bending stresses, and we wrote that in terms of sigma most likely, and that's going to be equal to a bending moment at any section along the length of the beam times the distance from the neutral axis to the fiber that you would like to calculate stresses at, divided by the bending moment of inertia for the axis about which bending is occurring. In our next few slides, I'd like to just go through some photographs to discuss a little bit more about what we mean by a beam, to get a real-world sense of what beams might look like. Beam is a really generic term meaning any member that's being placed in flexure, such that the primary stresses that member is experiencing are flexural stresses. So that might include a ruled shape or a joist. This photograph includes both. You see that we have a rolled shape being used as a beam or a girder in this direction, and then in the opposite direction we have open web joists also being used as a flexural member. Now we're going to, or maybe you already have discussed joists in lab at this point, and we're going to leave our discussion of open web joists for the lab. We're going to limit our discussion in Lesson Plan 6 to the use of rolled shapes as flexural members. So for example, we'll be looking at a beam that looks very much like this one and solving for its flexural capacity. This schematic shows a floor layout in a typical steel frame structure, and it's handy because it's gone through the process of labeling some of these elements. And you've seen diagrams like this in lab. Here the exterior element in flexure is being labeled a girder, and one of the interior flexural members is being labeled a fill beam or a filler beam. So usually on top of the fill beams, we'll see the presence of a steel deck or a concrete slab or both, and these are going to act as loads across the fill beams such that we have really distributed uniform loads across most of the fill beams, and then those fill beams frame into exterior girders as point loads. Now, one of the things we're going to spend a considerable amount of time discussing in future lesson plans are the impact of these steel decks or concrete slabs that are resting on the top flange of the fill beams. If an appropriate connection is made between the decking and the top flange of the fill beam, we can expect that steel deck to provide some lateral resistance to the top flange of the fill beam. And what that does is when the top flange is the flange resisting compressive stresses, that's going to limit the tendency of those beams to buckle. And so the presence of that steel deck and concrete slab can be very important to us in normal building structures. Here's another photograph of a steel frame structure. One thing that I think is obvious when you look at this is the aspect ratio between the beams and the columns. And it is indeed typical to see the beams have a greater depth than the columns. This aspect ratio may be a little bit skewed towards the size of the beams, but it is common for the depth of the beams to be somewhere on the order of a W21, W24, and the depth of the columns to be more on the order of a W12 or a W14. So that is somewhat typical. Again, we see the use of open web joists on the roof level of this structure, and that also is not atypical. Here's another example where we see a series of beams framing into columns that are considerably less in depth than the beams. So here's one of our beams. We also have a series of different roof beams, and it looks like purlins. And then this is the KU Structures Testing Lab over on West Campus that we went and visited. You can see here we have a series of different beams at different story heights, as well as on the roof level we have girder type beams and fill beams. And again, here's that structure. And this structure is a little atypical as compared to some of the other photographs that we looked at, in that the size of the beam is smaller relative to the size of the column. And one reason for that in this photograph is we're really not going to have floor loads framing onto these beams. These beams are really intended to be axial members. In fact, when you look at the roof beams, you see that the roof beams are going to be much closer in terms of depth to the depth of the columns. And that makes more sense because those beams are going to actually be carrying flexural stresses. Here's another photograph showing the beams, in this case resisting mostly axial loads and framing into the columns. Okay, so what are the internal forces that a beam is expected to resist? This is an important question. So we would expect a beam to be able to resist shear forces. And there's our positive sign convention for shear. Down on the left face of a section and right on the right face of the section, shear should be acting upwards. We expect there to be internal bending moments, and our positive sign convention is such that those moments are producing compression in the top fibers of a beam and tension in the bottom fibers of a beam. And then we also expect that there is potential for axial forces to develop. So I'll use the symbology H for horizontal forces, and we take these as positive when they are acting outwards from the exposed face of a section. So I think it's useful at this point to brainstorm a list of the different ways that we might expect a beam to fail. And I'm going to divide this list into three categories. Modes that a beam can fail in flexure, modes that a beam can fail in shear, and a catch-all category called other. Now those of you who have taken or are taking a class in concrete design This list is going to be significantly different than a list like this that you might generate for concrete. And that's because concrete is often limited by failure strength of the material. And concrete is going to be very weak in terms of shear. And so we're going to see a long list under shear. That's going to be the type of mode that concrete beams are most sensitive to. For us, steel beams are going to be much more sensitive to flexural failure modes on a more global level than on a material level. And so we will see less emphasis placed on shear failures when we're talking about steel and more emphasis on some other global flexural modes. The first flexural mode that I'm going to list is yielding. We can fail a steel beam by applying a moment large enough such that the cross-section yields all the way through its depth. And when it does that, we term the moment that produces yielding all the way through its depth the plastic moment. In other words, we have taken the material from the top of a beam to the bottom of a beam, and we have yielded every fiber along that depth. So that is a plastic moment. We can also experience local buckling failures due to bending. And this can occur in either a flange or a web. So we'll need to be able to design to resist local buckling. And then we can also see a mode of failure in which we have a combined mode of flexure and torsion. And when this combined mode occurs in bending, we call it lateral torsional buckling. I'm going to abbreviate that LTB very commonly. When we talk about failure modes in shear, we usually divide our conversation into shear yielding, and this is going to be our concern when we have shapes that are stocky enough such that they can actually develop the yield strength of the material. If the shape isn't very stocky and we are concerned about shear, then we're going to be checking shear buckling. And then in our other category, I'm going to add web crippling or web yielding. And the differentiation between these two limit states is based on the stockiness of the cross-section, primarily on the stockiness of the web. And these are localized failure modes. So web crippling and web yielding are going to be checked whenever we have very large concentrated forces applied over a length of the flange. And so we will talk about each of these 6 different limit states in detail over the next 3 lesson plans. The 2 that we're going to focus on in lesson plan 6 are yielding, the development of the plastic moment capacity of a beam, and local buckling. We're going to talk about lateral torsional buckling in lesson plan 7, and we'll talk about shear and web crippling and web yielding in lesson plan 8. So I do want to, at this point though, discuss at some level the occurrence of buckling in beams, because I don't think it's intuitive. And we talk about columns, and I think it's very intuitive that a column is going to be susceptible to stability failure modes. A column is going to be susceptible to buckling. But a beam, I'm not sure that makes sense. Why wouldn't a beam just fail by yielding or by some sort of local buckling failure mode? And the reason that we have to worry about buckling in beams is that when we consider the distribution of flexural stresses along a beam's cross-section, so if in this figure I'm showing an I shape, and here I'm sketching a cross-section view. If we are in positive bending, I can expect compressive stresses at the top and tensile stresses at the bottom. And that means that the whole portion of the beam above the neutral axis is in compression. So that portion of the beam's cross-section is really acting a lot like a column. So that means the portion of a beam that is resisting compression is going to be susceptible to instability. And we have to design the beam such that we keep instabilities from occurring. So this is how we're going to progress through our discussion of flexural members. We're going to start by assuming that we have no instability, no buckling. So we're going to start our discussion in this lesson plan by assuming we have no lateral torsional buckling. And this will be true for beams that have continuous lateral support. All I mean by continuous lateral support is that the compression flange of a beam loaded in flexure is restrained against lateral movement along its entire length. So let me see if I can sketch a little rolled shape. Let's say this guy is in flexure. If I'm assuming continuous lateral support, I'm effectively saying that I have braced the compression flange along its entire length such that that flange cannot move to the left or to the right. It has no means of kicking out and failing in torsion. So that forces a deformation mode along pure strong axis bending in this case. Now, as we figure out some of the fundamentals for flexure, we're going to start removing that continuous lateral support, and we're going to consider what happens when we do have lateral torsional buckling. So our next step will be to consider the case of lateral torsional buckling, and we're going to continue looking at beams that have braces, but we're going to spread those braces far enough apart such that we do have to worry about buckling occurring in between those brace points. And then finally, after we get all that figured out, we're going to consider beams that are susceptible to lateral torsional buckling where we have really, really long unbraced lengths between brace points. So we'll consider the case where we have no braces and very large unbraced lengths. I'm going to use L sub B to designate unbraced length. So if I was going to draw a similar sketch as above, except this time from an elevation view, here's a simply supported beam. And I've simplified my rolled shape as being just a straight line here. It might be the case if I have a brace acting at the far left and the far right. So if I was going to draw the top figure that way, there's my simply supported beam. I would have continuous lateral support along the entire length. And if I look at this intermediate type of beam that we're going to be considering, maybe I have braces at the end and brace at the middle. Now when I sketch a brace like this, it's a lateral brace. It's doing nothing in terms of vertical deflection. The beam can still deform vertically the same as it wants to. However, it is restraining deformations in and out of the page. Okay, so everyone remembers the column solution space plot that we looked at a number of times. This is a similar form of presenting information as we saw for columns, except this time it's for beams. When we talk about beams, we have a couple of different limit states that can control in flexure, and we said that one of those is lateral torsional buckling and another is local buckling. Well, both of those are buckling failure modes. So we could present a solution space like this for either of those failure modes. This one is for lateral torsional buckling. So to draw this solution space, I've assumed that flange or web local buckling is not controlling the strength of the beam. And when that is the case, when flange or web local buckling is not an issue, that means we're talking about a compact cross section. So to draw the solution space that I have sketched here, I'm talking about a compact cross-section, meaning it's not susceptible to local buckling, and yet we're looking at the range of lateral torsional buckling behavior that this beam could experience. So on the y-axis, I'm presenting moment capacity, nominal moment strength, M sub n, and this is a new way of talking about capacities. When we talk about capacities for columns, we talk about axial load capacities, and we designated that with the letter P. So our nominal capacity for a column was P sub n. For beams, it's traditional to talk about capacity in terms of moment strength, and so we're switching to the letter M. And when I use a subscript of n, that means we're talking about the nominal moment capacity. So I have nominal moment strength on the y-axis, and then on the x-axis, I'm plotting unbraced length. An unbraced length is just the distance between brace points. So here's my simply supported beam, and I have a number of different lateral braces. Those distances are unbraced lengths. So we could call that unbraced length 1 and unbraced length 2. So you would figure out the controlling unbraced length, and that would tell you what sort of behavior your beam is going to be governed by with respect to lateral torsional buckling. For very short unbraced lengths, we're going to be governed by the plastic moment of the material, or of the cross-section. So we have this plateau region for unbraced lengths that are relatively small. When we look at very, very large unbraced lengths, our behavior looks a lot like the elastic buckling portion of our column curve. And we are in a region of elastic lateral torsional buckling. When I have intermediate unbraced lengths, we're going to be governed by inelastic lateral torsional buckling, and the behavior is going to be approximated by a straight line in between the plastic moment strength and elastic lateral torsional buckling strength. Now the values of unbraced length that these correspond to, the junction between inelastic and elastic lateral torsional buckling is going to correspond to an unbraced length L sub r, and the junction between the plastic moment strength and inelastic lateral torsional buckling is going to be defined by an unbraced length L sub p. So maybe it's surprising that this solution space looks almost exactly the same as it did for columns, but maybe it shouldn't be surprising. Again, we talked about the fact that the portion of a beam above the neutral axis when it's in positive flexure or below the neutral axis when it's in negative flexure is going to be in compression, and that section of the beam is going to be acting a lot like a column. So it makes sense that the behavior of the beam is going to be pretty similar.